Hello everyone. So in the last session, actually we completed inverse Laplace by taking the properties or by using the properties. Now here we are going to start a type 2 examples where we'll find the inverse Laplace transform by by this partial fraction method. Inverse Laplace transform by a partial fraction method. So already I given one video on the prerequisite formulas that you should know the how to write a partial fraction mainly. So if you are good in the partial fraction, this is one of the simple method that you have. So there are four types of a partial fraction in inverse Laplace transform. Whenever we have linear and distinct factors in the denominator, that is a case 1. Case 2, we have linear and repeated factors in the denominator. Case 3, we have linear and quadratic factor, and the last case is only quadratic factors appear everywhere. There is no linear term present in the expression. So if you understand the four examples of each of these type, yes, you can find the Laplace or inverse Laplace of any given rational function. Okay, of where the denominators have either linear or a quadratic factor. So we'll see one example, at least one example of each type in this video, so one by one. So we'll start with the first example. Suppose we are interested to find out the inverse Laplace of the first example. Let me find out L inverse of 1 upon say s square minus 5s plus 6. Okay, the case is you'll observe the denominator is s square minus 5s plus 6, and we have the factors for this quadratic equation. Whenever the factors are available, write the factors and do it by partial fraction. If the factors are not possible, you can go for complete square and you will find the inverse Laplace. So in this case, this same equation is written in a factor form. So I will start a solution actually. We'll start this solution, and the solution is L inverse of L inverse of 1 upon the factors of denominator are s minus 2 and s minus 3. Next step starts a partial fraction. Now what is the case we are coming across? We have a linear and distinct factors in the denominator. So the partial fraction of linear and distinct factors in the denominator is say a upon the first linear factor plus b upon the next linear factor, and only two are there. So number of constants involved in the partial fraction is equal to the number of factors in the denominator. Right now two factors are there, s minus 2 and s minus 3, so a and b are there. Once we write a partial fraction, the most important part of a partial fraction method is getting the values of these the constant a and b. Now to find out a, we use a shortcut method. Now what is a shortcut method? To get the constant a, whatever the denominator of a, that denominator ignore from the original given function and write a remaining. So if we ignore the denominator, which is s minus 2, from the entire given function, we left with 1 upon s minus 3, where we'll put the value of s by equating the denominator of a only to the 0. So if we put s minus 2 equal to 0, we get s is equal to 2. So if we put s is equal to 2 here, so we get 1 upon 2 minus 3, and the value of a we get as a minus 1. Okay, so this is the simplest method of getting the values of constant, and that is a shortcut method. So next, to get the value of a b, we do the similar shortcut method. So just ignore the denominator of a b from the given function. We left with 1 upon s minus 2, and where we'll replace s by equating the denominator of b to the 0, that is s by 3. So we got the answer as 1 upon 3 minus 2, which is 1. So we got a and b. So the next step, yes, we will just replace these values of a and b. So we got L inverse of the value of A is a minus 1 and the value of B is plus 1, and the last step is left now. We are going to use a standard results. We know the inverse Laplace of 1 upon s minus a. 1 upon s minus a is e raised to at. So in this case minus e raised to 2t. Why this minus? Because already there is minus in the numerator. Plus inverse of 1 upon s minus 3 is e raised to 3t. And that is the end of a question. We got the answer, and this one is our final answer. So see how inverse Laplace of a partial fraction is one of the simple method that you have. So straightforward, find the values of constant of a partial fraction and take the inverse Laplace by a standard result. Okay, I hope the first example is clear. I will move to the next question then. Let me start a new example. Example 2, say we have to find L inverse for s upon 2s minus 1 into 3s minus 1. Our aim is to get the inverse Laplace of this. So in the solution, step number 1, again observe the same case is there. We have linear distinct factor in the denominator. So it is like case 1 only, where we can write out a upon the first linear factor plus b upon the second linear factor, and that about a partial fraction. Next part, we mainly calculate the values of a constants. To get the value of a, ignore this 2s minus 1 and write down the remaining. The remaining part is s upon 3s minus 1, where we'll put s is equal to, equate the denominator of a to the 0, you'll get 2s minus 1 is 0, so s is a 1 by 2. And if you replace s by 1 by 2, you will get 1 by 2 divided by 3 by 2 minus 1. So 1 by 2 upon 3 by 2 minus 1 is again a 1 by 2. So it is 1. So value of a is 1. Similarly, the value of b we can compute as s upon, we are ignoring 3s minus 1 now. Only 2s minus 1 is in the denominator then, and we'll put s by 1 by 3. If we put this, you will observe it is 1 by 3 divided by 2 by 3 minus 1. So 1 by 3 upon minus 1 by 3. So b is a minus 1. So we got a and b. So just we are going to replace it now in the function and we'll take inverse. So step 1, the value of a is 1. So it is a 2s minus 1, and the value of b is a minus 1. So this one is the case where you cannot we cannot apply the standard result directly. The requirement is 1 upon s minus a is there. So what is a simple thing that we can do it to make the coefficient of s as a 1? We can take that 2 as a common. So it is 2 into s minus 1 by 2 minus, and from the second term we can take 3 as a common, s minus 1 by 3. And the last step now, this 1 by 2 is as it is. Inverse of 1 upon s minus 1 half is e raised to t by 2 minus 1 by 3 e raised to t by 3, and that is the end of a question. This is our answer. This is the answer. Okay, so just we completed 2 examples. Both the examples are on linear distinct factor. And it is very straightforward. Both the case, we find out the constants by a shortcut method and we got the answer. Let me move to the next case now. Case 2, where we have linear repeated factor. Suppose we come across a linear repeated factor and we are interested to get the inverse Laplace. So in the third case, you will observe, say example is, we have to find out L inverse of s cube. Okay, I will take a numerator as say s minus 2 upon s cube into s plus 2. You will clearly observe in the denominator s cube is there. That means s equal to 0 is a factor repeated thrice. So these are three factor and this is s plus 2 is a fourth. So number of constant is equal to number of factors. So total 4 constant will be there in a partial fraction. So step 1 is important to write the correct partial fraction. So in the first step, we can say, okay, let I say here, let s minus 2 upon that s cube into s plus 2 is a upon s plus b upon s square plus c upon s cube, and lastly that d upon s plus 2. So you'll observe there are 4 constant a, b, c, d, which is equal to the 4 factors, and our aim is to get now these values of these 4 constant there. Now to get the values of this 4 constant, yes, we can use a shortcut method, but to use a shortcut method for a, you will observe if we ignore just only one s, if we ignore only one s from the denominator here, we left s square and then we put s by 0. So 1 upon 0 is undefined. So value of a and b, will not get by a shortcut method because the method fails there. But yes, we can continue the shortcut method for getting c and d. So to get the value of c, you will observe we have to ignore the denominator of c from the given function. So we'll ignore s cube. We're left with s minus 2 divided by s plus 2 only, where we are going to replace s by 0. You will observe, equate the denominator of c to the 0, s is a 0. So if we replace that, you will observe minus 2 upon 2, which is a minus 1. The value of c is a minus 1. Now, to get the value of a d, the similar thing, we ignore that s plus 2 factor, we left with s minus 2 divided by s cube only, where we'll replace s by minus 2, denominator of d to the 0. So it is a minus 4, numerator will become minus 4 upon minus 2 cube is a minus 8, and value of d comes as a 1 by 2. So we got c and d by a shortcut method, but yes, the values of a and b helps here to get by a shortcut method. So what we have to do it, there is no option other than cross multiplication. So whenever shortcut method fails, cross multiply. We are cross multiplying by this denominator on the both side. So what we get here, this is actually this equation 1 gives us s minus 2 is equal to the value of a. Yes, we not calculated. So a, see when you cross multiply this factor, one s get cancelled, you left with s square into s plus 2 plus b into, now one that s square gets cancelled, only s into s plus 2 left. The value of c we already calculated is minus 1. So minus s cube get cancelled. We left with just plus s plus 2. And the last one, this is actually s plus 2 only. And the last one, the value of d is 1 by 2. So it is 1 by 2. S plus 2 will get cancelled. We're left with s cube only. So this is just by cross multiplication. Now the next task left here, to get the values of a and b from this equation. Remember, this equation holds for infinitely many values of s. And what are the simplest value that we can put in this equation? That starts always from 0. So you can put s by 0, then s by plus 1, s by minus 1, then plus 2, minus 2. But you'll observe already two values are used. Already two of the values are used. Which are that? So you'll observe the value s equal to 0 is used, s equal to minus 2 is used. So we have to write new values other than that. So we'll take s equal to, now 0 is used, and next simplest values are plus 1 and minus 1. So we'll replace that. So if we put s by plus 1, we get one equation. And if we put s by minus 1, we get another equation. You'll observe when s is a 1, you get minus 1 is equal to 2, that is a 1 plus 2, actually 3a plus 3b and minus 3 and plus half. So what we done, just we replace s by 1, and this gives us the equation for a plus b. After simplification, cross check what will be the value. This is actually minus 3 plus half is minus 6 plus 1 is minus 5 by 2. If you take this side, minus 1 plus 5 by 2, minus 1 plus 5 by 2 is uh, 3 by 2, 3 by 2, and 3 gets cancelled. So a plus b is 1 by 2. You can check, you can cross check. Similarly, when we put s is equal to minus 1 now, you get another equation. Minus 1 minus 2 is a minus 3. Now here it is plus 1, so it is minus 1 square is 1. So just a. This is a plus 1 minus b. Next, minus 1 plus 2 is a plus 1, so it is a minus 1. And the last one, minus 1 cube, is minus 1, so it is a minus half. Minus half. So this gives us the value for a minus b as a minus b is equal to, this is actually minus 3 by 2, and if you take on the other side minus 3 plus 3 by 2, so minus 3 sorry, it is a minus 3 by 2 plus 3 by 2 minus 3, yes, minus 6. Okay, do it on the rough and write this value. Do it. So I will do it in the rough. Minus 3. First I will check whether the equations are correct. So this is a minus b is a correct. So here we replaced s by minus 1. So minus 1 plus 2 is a minus 1 again, correct, and minus half, that is correct. So minus 3, and this is minus 3 by 2. So this comes as a 3 by 2. So minus 6 plus 3, minus 3 by 2 only. Okay, so you got a minus 3 by 2. Now if you add these two equations, you will observe when you add, you will get bb gets cancelled. 2a is equal to 2a is equal to minus 1. So 2a is equal to minus 1. So a is 1 by 2 or minus 1 by 2. So these two equations together gives us a as minus 1 by 2. If a is a minus half, is b is a 1. Now we have a and b, already c and d calculated. So by 1, the last step we left now. This is the most lengthy task actually in the partial fraction that you have, and you will observe just by equation 1 again we get L inverse of the value of a, we calculated minus 1 by 2, minus 1 by 2 into 1 by s. The value of b is 1, so 1 upon s square. The value of c that we calculate is minus 1, so minus 1 upon s cube. And the last one, the value of d is a plus 1 by 2, which is 1 upon s plus 2. Just we replace the values of a, b, c, d in that equation 1. And here is the answer now. This minus 1 by 2 is a constant. We know the inverse of 1 by s is a 1. Okay, inverse of 1 by s is a 1. Then inverse of 1 upon s square. Now inverse of 1 upon s raised to n plus 1 is a t raised to n upon gamma n plus 1. So s raised to n plus 1. N plus 1 is a 2, so n is 1. So t raised to 1 upon gamma 2, or t raised to 1 upon 1 factorial. So I will write it as a plus t raised to 1 upon 1 factorial. That's one. And next is minus t square by 2 factorial, and the last one plus 1 by 2 inverse of 1 upon s plus 2 is e raised to minus 2t. That is the end of a question. Just you can replace the values of these factorials there, that 2 factorial is 2 and 1 factorial is 1, and that is the end of a question here. So this is one of the lengthy example only. Whenever there is a repeated factor, the question becomes little lengthy there, and right now there are 4 constants, so that way it becomes little lengthy there. That's example 3. We'll move to the next then. Here the example 4 now. Question number 4, where we want to find here the inverse Laplace of linear and quadratic factor. Say we have one linear and a quadratic factor. I will take here 1 upon, say, s plus 1, s plus 1 into s square plus 4. A very simple function taken. You'll observe one is a linear, other is a quadratic term, and we want here inverse Laplace of this. So step number 1 in a solution, always we write a partial fraction. So let 1 upon s plus 1 into s square plus 4 is equal to a upon that linear factor plus, remember the partial fraction of a quadratic is we should have linear term on a numerator, bs plus c upon s square plus 4. And now our aim is to get that a, b, c here. Out of that, again the value of a, whenever linear distinct factor is there, you can find out the value of that by a shortcut method directly. So here a is equal to, ignore all remaining term. So 1 upon s square plus 4, you ignore that s plus 1 actually, and replace s by minus 1. If you replace s by minus 1, you will get 1 upon minus 1 plus 4, 1 by 3. Is it? Sorry, my mistake. We are replacing s by minus 1. Minus 1 square is 1, so 1 by 5. 1 by 5. 1 upon 5 is the value of a. To get b, s, b and c, again that shortcut method fails. So by 1 cross multiply, we get 1 is equal to a times, yes, sorry, my mistake again, the value of a we already calculated is 1 by 5. 1 by 5, that is a, s plus 1, we are cross multiplying, so 1 by 5 s square plus 4 left only, plus bs plus c, bs plus c into that s plus 1. My mistake. Now to get the values of b and c, we should replace two values for s. Already minus 1 value is used. Simplest values start with a 0. So s is 0 and s is 1. That is the best two values that we have. So I will start here by putting, I will put s by 0. If we put s by 0, you will observe we get 1 is equal to, this s is a 0, it's 4 by 5 only. Then this b is b into 0 plus c, and this is 0, so plus just c only. So we got the value of c as a minus 1 minus 4 by 5. What is 1 minus 4 by 5? So 5 minus 4 is 1, it is 1 by 5. So value of c we got as a 1 by 5 directly. Similarly, now minus 1 is already used here, so we are going to replace s by plus 1. Don't substitute repeated same values, you can't get the new constant then. So when we put s by 1, so 1 is equal to, now it is a 1 plus 4 is a 5, 5 by 5 is a 1, plus b plus 1 by 5, that is the value of c, and this is to 2. So that only we have to simplify. So this 1 gets cancelled. You will get actually 1 minus 1 is a 0. So b plus 1 by 5 is a 0. Value of b is minus 1 by 5. B is minus 1 of 5. So we got a, b, c now. We have a here, we have b here, and the value of c is, c is there and b is there. So by 1 now, the last part, we have to say L inverse of, replacing ABCs. The value of A is 1 by 5. So 1 by 5 upon S plus 1. The value of B, is a minus 1 by 5. So minus 1 by 5 S. If you take a separate division, that's a better, you will get it better. So S square plus 4. So this is actually the value of B plus C. C is again 1 by 5 upon S square plus 4. The last step now, 1 by 5 is a constant, that is the value of A, and inverse of 1 upon S plus 1 is e raised to minus t. This minus 1 by 5 is again a constant as it is s upon s square plus 4. S upon s square plus 4 corresponds to cos of 2t. And the last one here is always a problem, that is it is a 1 by 5 s square plus 4, so it is a constant is there, so that constant 1 by 5 as it is, but 1 upon s square, so we require 2 in the numerator, so we'll multiply by 2, divide by 2. So instead of 1 by 5 you should write it is a 1 by 5 into 2 is a 10, so 1 by 10, 1 by 10, and it is a sine 2t. That's the end of a question. So answer is here. Okay, so that about the fourth. Now one last example and the last case is left. We'll move to that, which is next example. So the last question that I want to show you here is quadratic terms everywhere. Whenever you come across this situation, say s square divided by s square plus 4 into s square plus 9. You will observe wherever s is appeared, it is in quadratic term. Main important thing, there is no linear term of s. So there is no s square plus 2s, or there is no s plus 9. So everywhere is a quadratic. So this is a very simple example and can be solved by like case one where we seen linear distinct factor, exactly same way. So for a solution, what we'll do it, we will proceed as L inverse of, we use a simple partial fraction only. There's no need to write as plus b, because s square, everywhere s square is appeared. So it is a linear in s square. So and b upon s square plus 9. So simple partial fraction work here. Now what we'll do it, to get the value of a, to get the value of a, we'll put s square by, let I show you here, then only you'll understand. So a is equal to, actually we ignore this term s square plus 4, we'll have to s square upon s square plus 9, and we replace s square, only s square by minus 4, denominator equating. So it is a minus 4 upon minus 4 upon minus 4 plus 9 is a 5, minus 4 by 5. So we got that minus 4 by 5 is the value of a. Minus 4 by 5 is the value of a divided by s square plus 4. To get the value of a b, we take it as s square upon s square plus 4 by a shortcut method where we replace s square by minus 9, and we get a minus 9 by minus 5. So 9 by 5 is it? 9 minus plus 9 by 5. So plus 9 by 5 divided by s square plus 9, and that is the values of a and b. Now you'll observe here, to get this inverse s square plus 4, what is the requirement? We want 2 there. So 2 upon s square plus 4, we know the inverse is a sine 2t. So what should be done? So that 2 can be adjusted from minus 4 by 5. So I will write minus 2 by 5 here. Similarly, for s square plus 9, we want a 3. So 3 upon s square plus 9. So that extra 3 we want. So plus 3 by 5. And now the last step, it is a minus 2 by 5. Inverse of 2 upon s square plus 4 is a sine 2t. And inverse of 3 upon s square plus 9 is a sine 3t. And that is the end of a question here. So if you are very good in these 5 examples, whatever the 5 examples we covered, actually it covers all types, all variety of the inverse Laplace of a partial fraction. So there may be a little difference in the constants only, but these are the 4-5 examples, very important. You should understand how we return a partial fraction and how we solve. So this is the end of a question, and that is the end of your type 2 inverse by a partial fraction method. Okay, thank you.